Hello, welcome to my channel. My name is Maxwell and Omega. We are going through the introduction to algorithm question and answer. Question number 1, we have an array. We are asked to sort using the counting sort. Well, in the counting sort, we know that we need to build up an array of counts. Therefore, look at the array given and then look at the largest or the greatest number in the array, and in our case it is number 6. Number 6 will give us a hint on how big our array of counts will be. As you can see here, it's coming from array starting from index 0 going up to index 6. Therefore, we shall also use those indices to be able to tally or count the number of times each of the values appear in the original array. So therefore, we look at the number 0, how many times is it appearing here? You have 1, 2. So put 2. Come to number 1, how many times number 1 is appearing here? 1, 2. 2 times. Number 2, how many times? 1, 2. 2 times. Number 3, 1, 2. 3 times. Number 4, it only appears once. Number 5, 0 times. Number 6, 2 times. Good. After I've done that, the next step is the number of elements before each. Therefore, what shall do? We'll create another array C. We'll call it new C. We shall drop these 2 first here. Then 2 plus 2 makes 4. 2 plus 2 makes 6. 2 plus 2 makes 8. 2 plus 1 makes 9. 9 plus we come again. 2 plus 2, 4. 4 plus 2, 6. 6 plus 2, 8. 8 plus 1, 9. 9 plus 0, 9. 9 plus 2, 11. Okay, so this number 11 should be representing the number of items in our array. So if you count the number of items in our array, we find that the 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good, so we are in good shape. So let's go to the next step. Now we shall go through the iterations, and this time we shall start our array. Notice that J has been moving all through the array up to the end. Now at this point, the J, which is keeping track of the index, will be at number 2. So we check at number 2. We look at the array, the previous array. Number 2 is telling us that we should be at index. So we shall put 2 on the index 6, and we shall subtract 1 here, and the position will be 5. Therefore, we shall put 2 at the index 6 of the sorted array, of the proposed sorted array, and therefore we shall reduce the position 2 from 6 to 5. Okay. Then the next item in the array is 3, and 3 is in position 8. So we shall come and drop it at position 8, and also reduce from 8 by 1, it should be 7. Next item is number 1. You know, number 1 is at position 4. So we shall put number 1 at position 4, then we shall subtract 1 from 4, and we shall have 3. Move to 6. 6 is at position 11. So we shall come here and put it at position 11, and therefore subtract 1, find 10. The next item is 4. 4 is at position 9. So we shall come here and put that position 9. Then subtract 1, comes position 8. Next is position 3. Position 3 is previously position 3 is in index 7, so I shall put it at index 7, then reduce the index to 6, then go to 1 currently is at position 3, so I shall put that at position 3, then reduce to 2, 0 is at position 2, so we shall put it at position 2, then subtract 1 from there, you get 1, then you go to 2 to the position 5, you put it at position 5 there, then reduce this to 4, then you come again back to 0, 0 is position 1, we shall drop it there, and we shall subtract 1 from that, it will be 0, then 6 is at position 10, we placed at that point, and reduce to 9. Then eventually at this point, we find that we have sorted our array using the counting sort algorithm. Question number 2 is, suppose we were to rewrite the for loop of the header in line 10, and this is a this format. This is a sample of line 10 of the counting sort. Suppose we rewrite it to this line of the for loop. If we change the for loop to this, how will the algorithm behave? And if it is modified, is the algorithm stable? So the question you're asking. Well, in essence, the solution is it will work properly, but it will not be stable. Why would it work properly? Notice that what you're proposing is change the for loop, say from 1 to the length of the array. That means that it will be arranging it in the reverse order. It will be arranging it in the reverse order, unlike the way we've been doing, that it gets it from the length to 1. In that way, it arranges it well. But if you start from 1 to the length of the array, it will do it in the reverse order. The elements that appear on the sorted array. Number 3 says, starting with the procedure Max-heap, we'll write the pseudocode for the procedure MIN-HEAP A for semicolon I, which performs the corresponding manipulations of the MIN-HEAP. How does this running time of MIN-HEAP? How does the running time of MIN-HEAP compared to the Max-heap? So basically, the question here is that how will the first of all is to modify the algorithm from Max-heap to MIN-HEAP and see what the running time will be. So our solution is here. So this is the pseudocode for MIN-HEAP. Well, pretty much as you see, we start by creating that function MIN-HEAPIFY. Okay, so there is Max-heapify and MIN-HEAPIFY. Okay, so this is what we shall do now. Create the function MIN-HEAPIFY, and this is the array A, and we have the index I. Then we will split the left and the right, L being the left and R being the right. So then we have the if condition here. If L is less than the length of the array, length of the heap size of A, and the value at A index L is less than the value at A index I, then the smallest is L, else the smallest is I. Another condition is that if R is less or equal to A heap size and the value at AR is less than the value of AI, then the smallest is R. If the smallest is not I, we exchange AI with the smallest. Then you perform the function MIN-HEAPIFY of the array and be able to be sorted. So pretty much this is how it looks like. Not so much different from the Max-heapify, but for the Max-heapify, at this point you have the comparison where it is greater than, not less than. So for MIN-HEAPIFY, we'll be looking at less than AL less than AI, then AR less than AI. For Max-heapify is greater than. Pretty much when it comes to the running time, it's pretty much the same. Yeah, that this time you're focusing on the smallest value, right? And with the Max-heapify, you're focusing on the largest value in the array. So this is to illustrate the operation of Build-Max-Heap on the array A given there. So we know that the algorithm of Build-Max-Heap, that's the algorithm to get the heap size, which is equal to the heap length, equal to the length of the array, sorry. Then for I, then you divide the length of the array by 2, and then down to 1. Then you perform the heapify. You call the heapify function and run it at line 3. So let's see how this looks like. So let me plug in our array 5, 3. So you can look at you can count the number of items in the array: 2, 3, 4, 5, 6, 7, 8, 9. So these are the tree and the branches and the leaves. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, you start plugging in the values: 5, 3, 17, 10, 84, 19, 6, 22, 9. So as you have seen that the second step after getting the size of the array, or the length of the array, the heap size, now it's time the I will begin at length divided by 2. So 9 divided. So when you divide 9 by 2, you get 4.5, and therefore you take the position 4 of the tree. So you know this is 1, 2, 3, 4. So that's where I begin from to do our algorithm. After you've reached there, you look on the left and on the right and pick the greatest value. So we will see that 22 is big, then we'll be able to swap the 2. 22 will go up, 10 will come down. Then I will decrement by 1, so I will move to index 3. Also index 3 will look to the left and find if it is a bigger value. Then they will swap. It will be swapped. Then I will reduce by 1. Then it will be at index 2. So Index 2 we have value 3. 3 will check 22 and 84, which is greater 84. It will swap with 84, push it up. Then the index will be reduced by 1, so it will be at position 1. Then it will look at at the root. Then we look at 84 and 19. 84 is big, it will be pushed up. 5 will come down. Then again 5 will look. Is 22 and 3 is great. 22 will be great, it will be pushed up. 5 will be here, then 5 will look again and check 10 and 9, which is the greatest. 10 is the greatest, will be pushed up, and 5 will be brought down, will be swapped there. Therefore, eventually we shall come up with, we shall be able to build this tree, which is already sorted. As you can see, all the leaves and less in value compared to the parents. As you can see, the heap is sorted. We have this final question. Use the master method to give the tight asymptotic bounds for the following recurrences. You have A and B. So the solution for 5A, we have that. Then we plug in A and B. Fn is n. Then plug in that, we find it is half. Then we compare half and f, we find that n to the power half is polynomially smaller than fn, which is a decreasing geometric series. Therefore, that gives a hint that we're going to use case 3 of the master theorem. And the epsilon that we approximate to add is a half. Therefore, we come and also check the other the regularity condition, and again we see that it also satisfies that when you plug in into the equation, it will be less than the constant multiplied by fn for some 0 less than c and c less than 1. Then the time complexity of the case 3, or the running time for case 3 master theorem is theta fn, and therefore for our case here it will be theta n. That will be the running time, or the time complexity. 5b, we have this question: Tn is equals to 2t n divided by 4 plus n squared. Then you plug in the function. You plug in a and b into the log, into the power log 2 base 4. It will be n to the power half. Again, we compare the power half and the fn. Again, it's polynomially smaller than n squared. So this will be case 3, and the approximate epsilon will be 2 over 3, 3 over 2. This epsilon value that we approximate, that will be able to be required to 3 master theorem. Then the regularity condition will be also checked at this point, and we find that also it is satisfying. Then when you plug in into the time complexity of the running time of case 3, you find that yes, we are having our running time as theta n squared. We have reached the end of our question and answer. Thank you very much for watching. See you next time.